I am Devasena. In this lecture, we are going to discuss about full wave rectifiers. This topic is present in the subject Electronic Circuits 1. Before going to discuss about the operation of the full wave rectifier, let us start discussing about the disadvantages of the half wave rectifier. The ripple factor of the half wave rectifier is 1.21, which is quite high. The maximum theoretical efficiency of the half-wave rectifier is found to be 40.6%, which is very low when compared to the full-wave rectifier. The DC current is flowing through the secondary winding of the transformer, which may cause DC saturation of the core of the transformer. To minimize the saturation, the transformer have to be increased accordingly. This increases the cost. The transformer utilization factor is very low, showing that the transformer is not fully utilized. Let us discuss about full wave rectifiers. The full wave rectifier inverts the negative portions of the sine wave so that a unipolar output signal is generated during both halves of the input sinusoidal signal. A full wave rectifier is a circuit which allows a unidirectional current to flow through the load during the entire input cycle, that is both the positive half cycle as well as to the negative half cycle. There are two types of full wave rectifiers. They are, the first one is a center tapped full wave rectifier and the next one is bridge rectifier. Let us see the operation of the full wave rectifier. In full wave rectification, current flows through the load in the same direction for both half cycles of the input AC voltage. It uses the center tapped transformer which provides equal voltages above and below the center tapped for both the half cycles. The voltage between the center tap and either end of the secondary winding is half of the secondary voltage. The center tap on the secondary winding of a transformer is taken as the ground or zero voltage reference point. The circuit uses two diodes which are connected to the center tapped secondary winding of the transformer. Diode D1 utilizes the AC voltage appearing across the upper half of the secondary winding for rectification, while diode D2 uses the lower half winding. The voltage between the center tap at either end of the secondary winding is half of the secondary voltage. Full wave rectifier diagram. In this diagram, AC input voltage is applied to the primary winding of the transformer. The secondary winding of the transformer is connected to the diodes. The terminal A of the secondary winding of the transformer is connected to the diode D1 and terminal B of the secondary winding of the transformer is connected to the diode D2. The output is obtained across the load resistor RL. During positive half cycle of the secondary voltage, the end A of the secondary winding becomes positive and end B is negative. This makes the diode D1 conducts while the diode D2 does not. That is, diode D1 is forward biased and diode D2 is reverse biased. Because of this, diode D1 conducts and diode D2 not conducts. The conventional current flow is through the diode D1 to the load resistor RL and upper half of the secondary winding. During negative half cycle of the secondary voltage, the end A of the secondary winding becomes negative and end B of the secondary winding is positive. This makes diode D2 conducts while diode D1 does not. That is, diode D2 is now forward biased and diode D1 is reverse biased. The conventional current flow is through the diode D2 to the load resistor RL and lower half of the secondary winding. The current in the load resistor RL is in the same direction for both half cycles of the input AC voltage. Let us see the input and output waveforms of the full wave rectifier. Now we will start analyzing the full wave rectifier. Let us consider an ideal diode assuming the diode forward resistance is RF is equal to 0 and the cut-in voltage is equal to 0. Hence, the diode D1 conducts for the entire positive half of the input cycle and diode D2 conducts for the entire negative half of the input cycle. Let us represent the AC input as V suffix I is equal to capital V suffix M sin omega t. Capital V suffix M represents the maximum value of the AC signal and omega its frequency. Let us represent the current flowing through the load resistance capital R suffix L is capital I suffix L, that is equal to capital I suffix M sin omega t. Let us obtain the average DC value. I average is equal to IDC, that is equal to area under the curve over a half cycle divided by base or period. IDC is equal to 1 by pi integral of 0 to pi IL d omega t. For the full wave rectifier, the output is obtained for both the half cycles. Therefore, the lower limit of the integration is 0 and upper limit of the integration is pi. This is equal to 1 by pi integral of 0 to pi Im sin omega t d omega t. That is, the value of IL is substituted here. After obtaining the integration, we get Im by pi minus cos omega t 0 to pi. That is, the integral of sin omega t is minus cos omega t. If we simplify the given equation means we obtain Im by pi cos pi minus cos 0. If we further simplify means we obtain Im by pi into minus 1 because the value of the cos pi is minus 1 and cos 0 is 1. Therefore, we obtain I suffix dc is equal to 2Im by pi. Similarly, V suffix dc is equal to 2Vm by pi. Now we obtain the RMS value of the load current, IRMS. IRMS is equal to square root of 1 by pi integral of 0 to pi Im sin omega t the whole square d omega t. If we further simplify means we obtain square root of Im square by pi integral of 0 to pi 1 minus cos 2 omega t by 2 the whole square d omega t, because the value of the sin square omega t is 1 minus cos 2 omega t by 2. If we further simplify means we obtain square root of Im square by 2 pi into omega t minus sin 2 omega t by 2. The lower limit is 0, upper limit is pi, because the integral of cos 2 omega t is sin 2 omega t. If we further simplify the above equation means we obtain square root of Im square by 2 pi into pi minus 0 minus of 0 minus 0. That is square root of Im square by 2 pi into pi. That is, IRMS value is equal to Im by root 2. Similarly, VRMS is equal to Vm by root 2. DC power output capital P suffix DC. DC power output capital P suffix DC is equal to capital E suffix DC into capital I suffix DC. That is IDC square into RL, because the value of EDC is equal to IDC into RL. Therefore, the value of P suffix DC is equal to 2Im by pi the whole square into RL. Here we have substituted the value of IDC as 2Im by pi. Therefore, we get P suffix dc is equal to 4 by pi square into Im square into RL. Now we are going to obtain AC power input capital P suffix EC. The AC power input taken from the secondary of the transformer is the power supplied to three resistance, namely load resistance RL, the diode resistance RF and winding resistance RS. The AC power input is equal to PAC. This is equal to Irms square into RF plus RL plus RS. We know the value of the Irms. That is Irms is equal to Im by root 2 for the full wave rectifier. Therefore, P suffix AC is equal to Im square by 2 into RF plus RL plus RS. Now we are going to obtain the rectifier efficiency. The rectifier efficiency is represented by a symbol eta. It is defined as the ratio of the DC output power capital P suffix DC to the AC input power capital P suffix AC. That is eta is equal to P suffix DC divided by P suffix AC, where P suffix DC is equal to IDC square into R and P suffix AC is equal to Irms square into RF plus RS plus R, where RF is the forward resistance of the diode, RS is secondary resistance of the transformer. Rectifier efficiency eta is equal to IDC square RL divided by Irms square into RS plus RF plus RL. For the full wave rectifier, the value of the Irms is equal to Im by root 2 and IDC is equal to 2Im by pi. And the value of RS plus RF is very less when compared to the RL. Therefore, we get eta is equal to 8 into RL divided by pi square into RL. That is, eta is equal to 8 by pi square. The percentage eta max is equal to 8 by pi square into 100. That is equal to 81.2%. Ripple factor. It is denoted by a letter gamma. The ripple factor is given by the general expression square root of Irms by IDC the whole square minus 1. For the full wave rectifier, the value of the Irms is equal to Im by root 2 and the value of the IDC is equal to 2Im by pi. Ripple factor gamma is equal to square root of Im by root 2 by 2Im by pi the whole square minus 1. If we further simplify this equation, means we obtain gamma is equal to square root of pi square by 8 minus 1. That is, gamma is equal to 0.48. This indicates that the ripple contents in the output are 48% of the DC component, which is much less than that for the half wave rectifier. Advantages of full wave rectifier. The DC load current and load voltage are more than the half wave rectifier. No DC current through the transformer windings, hence no possibility of saturation. The efficiency is higher, that is 81.2%. The large DC power output is obtained from the full wave rectifier. The ripple factor is less, that is 0.48 when compared to the half wave rectifier, because the ripple factor for the half wave rectifier is 1.21. Disadvantages of full wave rectifier. The PAV rating of the diode is higher. Higher PAV diodes are larger in size and costlier. The cost of the center tap transformer is high.